Okay. So hello everyone. Welcome back again to this India ML reading group. And today we have with us Amartya Roy, and we will be discussing about deep operator networks. But before Amartya starts the presentation, so I'll give a brief bio of him. Currently, Amartya is working at BOSS as a applied machine learning engineer. He did his master's in computer science and engineering department from Jadavpur University. He's passionate about mathematics. Currently, he is focused on building theoretical explanation and proofs for deep learning and deep neural networks. He's also very passionate in understanding the emergent interface between physics and neural networks. Along with this, he is also working with some groups on physics of AGI to discover the math behind LLMs. So over to you, Amartya.
Yeah,
You can
thank you.
share your screen. Yeah,
Yeah, 1 second. Just let me know if I am audible and visible.
yeah, you're audible. You're visible also. So you can share your screen.
Okay, 1 second. Let me know if screen is visible now.
Yeah, fine.
Okay, thank you for the nice introduction, Kisuleda. Okay, so for this entire presentation, I want to divide this entire thing into three parts. First is why the scientific machine learning is relevant nowadays. Second thing is what is DeepONet, and the third thing is what's our contribution in this DeepONet. Okay, so 1 second. Yeah, so this is the joint work with Dr. Anirbit Mukherjee. He is an assistant professor of University of Manchester in Computer Science Department. So our this paper has been now published in Transaction of Machine Learning Research. Okay, so from that subatomic level to the galaxy, from that Schrodinger to any black hole equation, PDEs are the utmost important thing. It's omnipresent. But as all of us from science background, we know like there are traditional solvers for PDE, Newton-Raphson's, and any there are many methods in that, Galerkin methods and all. But suddenly, from the 2017 or 16, some people started solving PDEs using neural net, and that creates a buzz like the LLMs are doing, and it covers, and many important journals are covering this thing, like as you can see in the screen, MIT News, that Quanta magazine, Nature Computational Science, many. So the question is, can neural net replace the traditional PDE solvers? If yes, why, and what's the backbone of it? So in this talk, I will not go into all of the methods of scientific machine learning. I will just go stick to one point, one element of scientific machine learning, that is DeepONet. So why DeepONet sounds very mathematical? That's it's very need to know first. So this is the schema of the DeepONet. So above there is a branch net and trunk net. So think like this: in branch and trunk, they are nothing but a, you can replace it with FNN or any kind of neural net. Probably you can use there a transformer also. That is a quite subjective question. But anyways, that can be any neural net. And we are doing the dot product or inner product of these two neural net. And what is the input of these two neural net? Okay, this is the critical thing. So these two parts are called branch and trunk. For the branch, we give the functions evaluated at some points. So these are the discretization of functional values. And the trunk input is the points where we want to ultimately find the solution of the PDE. So this is the point. Again, I'm repeating because this sometimes people confuse with this. This is the input where we want to find the solution of the PDE, and these are the points where we have evaluated the source function. This can be very different. Also same. There is no restriction of this. Okay. Okay. So here is an example of that. How to use a DeepONet. Suppose this is your PDE. and we know this PDE very well. This is the pendulum solving pendulum ODE, sorry, not PDE, yeah. And we need these three tuple to start with the DeepONet. This is the function evaluated or discretized at some sensor points. This is the trunk input, and this is the output. How we can get the output? Through numerical, traditional numerical solvers. All that we need. Okay. So if these three tuple we can get, we are good to go for the DeepONet. Now, one can ask, if we are already measuring through any traditional, then what's the point of using DeepONet? Think carefully. In many cases, we know the solutions of the PDE, but we don't know the underlying PDE. Their DeepONet can be a huge hit. So we know what are the solutions of the PDE at certain points, but we don't know the original underlying equation of the PDE. So by default, we know the Y and X. This we can generate. Then DeepONet easily can solve that PD without knowing even the PD. That comes to the next slide. So this is the loss actually. This is the loss. Our objective is to minimize this loss. Okay. So this was I was talking in the
Hello.
previous. Yeah. Hello.
Hi, Amartya. Sorry, I'm not from
Yeah.
math
Yes.
background. Could you
Yeah.
please
Yeah. Sure.
explain that? Could you please explain that equation that you have?
Okay. 1 second. What equation? This equation.
Yes, you had a pendulum equation, right? So how should I interpret this k, y, and yes?
Oh. Okay. 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 So okay. This is a pendulum. Okay. This is your source function, and you are measuring the how. Okay. So okay. How can I place with that? Let me give you one another example, or this example is fine. Okay. Okay. Think like this. This is your push. Suppose you are pushing a pendulum. So it will move like that. So this is your push. This is some function you are pushing through it. And this K and V are some constant. Now you want to, sorry, this K is a constant. Now you want to find the velocity. And this is the angular position of that pendulum. Is it clear? Or so basically you want to
So
find, yeah,
this two tuple is the angular position of the pendulum, is it?
yes, yes, yes.
Okay. So v is the velocity, and
Y is the
the
angular
second coordinate,
position of the angular
y
position of
is
the
the
OD.
angular position.
Yeah,
Okay.
yeah. And Y is the angular position
And
of the OD.
F is the force with which I push the pendulum.
Yeah, PP of F of T is the source function. That anything, push or something. Just for
Okay.
explanatory example, I give the push thing. Yeah.
Mhm. Yeah, yeah.
Okay,
Thank
right?
you. This helps. Yeah.
Yeah, thank you. Okay, so here was I. So okay, now given that loss function and this tuple, we can usually easily find the DeepONet solution. So DeepONet indicates if we have some sufficient number of valid input output pairs, then we don't need the knowledge of the underlying PD. That's the motivation for the real life scenario. There are a huge number of cases where you don't know the original PD. I can give you examples later, but there are many examples such cases. Now, in silico trials are buzzing in the UK, so there is a huge chance of implementing this DeepONet because in silico trial means some drug test using artificially organs, artificially simulated organs. So there you can have some solutions, how heart pumps and all, but you have not the critical heart structural PD. So there, this is a very important function. That can the place where this DeepONet will be very useful. And this is a very distinguished feature of this operator learning. Okay, but what is the backbone of this DeepONet? How can we assure that okay, the inner if we inner product if we do the inner product of this branch and trunk, then how DeepONet will approximately give us the solution? And here is the answer. So this there already all of us probably who are working in deep or neural net, they know there is a fundamental approximation, universal approximation theory for neural net. The same way in back 90s, I guess Chain and Chain gave this universal approximation theory for operator, and these guys, Karniadakis and Brown group, have modified this a little, and this is the backbone of DeepONet. How can we easily interpret this? Okay, so think like G is the solution operator. So if I go back to my thing here, you can think like here derivative is the operator and G is the derivative. Think like that. And our objective is to find the derivative operator. So N is our approximated solution, approximated operator solution, and G already we have. So now this theorem says that there exists some operator network which assures that this error will be below some threshold. So that's the motivation for using DeepONet. Okay. So this is some intuition how DeepONet works. So you already have noticed that branch and trunk. So it is the inner product of branch and this is the trunk. So how it is working? As I previously told, think like this. Branch is taking the discrete values of a function and trunk is taking where we want to find the solution of the PDE. So if we learn the trunk, that does mean we are finding p number of good solution in the whole functional space. And if we are learning the branch, then we are finding the good vectors in the span. So basically it's finding the coefficient and the trunk is helping to find the mapping of the functions. So this is how intuitively DeepONet works. Okay, now it comes how what is our contribution of this? This already exists. This all up to this 8th page already all these are exist. Now what's our contribution? Okay, I will put like this. There is suppose you know how much if you give 10,000 training data, then this LLM will work. And that will be huge blow. Correct. The same way, every researcher out there, our aim is to find a good neural net amount of training data. Like we need to find such training data relational with the neural net so that neural net works well. So we all are very curious to know the size of the neural net that are required to get the best possible performance, and that is by default scaling law. So there are lots of literatures in the scaling law, and like there are many literatures, but very few people have understood this scaling law properly. And this is our kind of we have tried to answer such questions of a size dependency for a specific kind of DeepONet. They are now here is a little twist. This DeepONet has a size constant. What is the constant? The constant is it has a bounded activation in the output layer. And we show that this common output dimension of two nets involved have to at least scale as the fourth root of the number of the available training data if we want to ensure that there exists an architecture in this function class where with the empirical error below a certain threshold. So what does it mean? If we have some training data, this relational training data, then we can have a nice DeepONet function, a nice which will give us a good error and it's bearable. So that's this theory says. So this is the first of a kind of its proof where we have been proved that this kind of architectural dependency is there, and if we ensure if we are ensuring this, then we can have a good neural net. Okay, that already I have said. And now there are some definitions need to be followed to understand this theorem properly. So this is a input output pair. These are SIPI and Y. This is a input output pair. SIRPI is the input and output is the Y, and our output is bounded by capital B and minus B to B. And this is the random variable which is dependent on the input output. And this is the definition of branch and trunk. That two functions where we are that inner product, we are doing that inner product. So this is a D1 to Q map and this is a D2 to Q map. Both the output dimension is Q, and this is the Lipschitz constant inequality follows that branch and trunk, and this is the weights. And here is the main thing: the weight vectors are bounded activations in their output layer. So this later will the theorem validates for this will be upper bounded by 1, but that does mean we can already use we can always use a sigmoid layer at the output, and that is the main constant of this proof. And this is the DeepONet where we are doing the inner product of branch and trunk. This is a formal setup of the DeepONet. Now, why we need a cover, I will come to that later, but this is the cover of this inner product. This is the cover of this DeepONet function. Like everything is same. There are two things, like we have already the weights in the previous slide. I have already shown these weights, right? These weights in the cover, the weights, like in the main function, the weights, and in the cover, the weights have a distance, and the distance is this theta by 2, and this is the covering space. And this actually the heart of the proof. This defines, like, this actually taken from a paper, this paper, Universal Law of Robustness by via Isoperimetry. This is a Sebastian Bubek's paper, and another one person was there, I forgot the name. And like they have told, like, these, if these two are the neural nets, then these two neural nets will follow this inequality. This is a kind of ellipse with bound. So this is the main heart of our proof. I will come to that later, how it influences our proof. Okay, so these are the some lemmas. This is the covering lemma through which we are measuring the covering number of branch and trunk weights. These are the cover shifting lemma. I will come to that because these will not make sense unless I go to the main theorem. And these are the value lemma. Okay, and this another lemma which helps us to find the value of this probability. Okay, now come to this. For any delta between this 0 to 1, what is our aim? Our aim is to show this, like, okay, probability of low error DeepONet exists, and that is the probability is high. That should be our aim, and that's our aim that we have proved. So how we can go through now? So what we have done, okay, so this lemma only valid for the cover of the DeepONet. So that's why we have defined the cover first. So okay, so now what we have done, we have measured this h theta value for using this lemma, and this comes out this. Okay, and this also, this value we have utilized for getting this value, we have utilized another lemma, this we called value lemma. Now we have got this, but everything is happening until now is the space, is the covering space, but we don't need that. We need all of these in our main h. So what we have done, this is the actual thing, cover shifting lemma. And to prove this cover shifting lemma, that Bubek thing, that J thing helps. That's why that's the heart of our lemma. That's all of the proof. So this is final outcome. What our final outcome says, like, this is the Q, the output, that output dimension layer, and this is the training data, and it depends with the fourth root of this training data. And this dependent on the weights and all. And how it valid, when it validates, when we have this branch and trunk net ending in sigmoid gates, and then it will ensure, like, this loss will be a good loss. We don't have to worry with the loss if we can do this. So in a snapshot, what our theorem proves, like, okay, now there another thing comes, like, if you can think carefully, you can think like, here scaling law can be done, right? So if I tell you n equals q to the power 4, q to the power square, q to the power 6, and we have done experiments for q to the power 3 by 2, q to the q square, q to the power 4, and q to the power 6. Now what we have observed, that for q to the power 3 by 2 means this will be 2 by 3. This doesn't hold. Monotonicity is breaking. Like we have taken, okay, let me quickly go to this. Yeah. So this we have done. What we have done, we have done 10 DeepONets, and for these 10 DeepONets, you can see everywhere the parameters will be more or nearly same. And we have this branch and trunk layer. and this m is constant over the all deep 10 DeepONets model. This is 40, and we maintain the ratio constant. Q by root n is constant. Now what we have observed, when we are doing this Q by root n setup, this monotonicity is exactly holding. When we are doing this for q by n to the power 1 by 6, means n equal to q to the power 6, there also this monotonicity holding. So, but when we are doing n to the power 2 by 3, there is it is not holding. So what does it mean? That does mean that q to the power 3 by 2, and between q to the power 3 by 2 and q square, the scaling law exists. If we can find that exact gamma, q to the power gamma, then we can ensure, like, with this ratio, if you increase the training data, if you increase your q with constant, with maintaining the parameters, then your training loss will monotonically converge. So that proves our theorem. So mainly what we have shown, two things. One, this is the first of a kind of proof where we have shown like architectural bound with relational data and the output layer. So if one have sufficient training data, and he can like manage the queue with accordingly tuning that data. Suppose you have some training data and you can tune your queue, you know, I need to set this queue, I need to set my architecture in this way, then you will end up with a good loss. So that's the first contribution. And the second contribution is the scaling law. The scaling law, if we can find the scaling law, if one can find the scaling law between 3 by 2 to 2, then already one can guarantee like the training loss will be monotonically converge. And there are many things now to do. One, we have assumed one constraint that the output layer will be bounded by sigmoid. So that should not be the case. It should be universal. Although this theorem doesn't depend on any any PD kind of setup. It is already, it is universal. But this constant is the only thing we need to remove. That's the next future work part. And the second is what I was telling in the beginning. Uh, in many cases, you don't know the underlying PD, and you need to solve it anyhow. And you know the solutions. Their DeepONet can be very useful. And if we know how much training data we need for that, then it will converge. Then we are done. And no traditional solver will do that. So there's the success of this DeepONet. Yeah. Thank you. Any questions now?
Yeah, so thanks, Amartya, for your talk. So, any question you want to have? Okay, so I personally have one question. So, this kind of PD solvers, what are the practical applications of these things in scientific domain?
Okay. Okay. So two things. First, think like this. You have a PDE, and okay, take some black hole PDE. Okay, and that black hole PDE nearly takes 2 days or 3 days. Solving that PDE nearly takes 2 or 3 days to get the solution. But using the scientific machine learning, it can solve within some minutes. That's the first thing. It's very speedy. But
Okay.
now people are telling like, okay, it's speedy, but there is some compromise in accuracy. For
Yeah.
that, we are developing these theoretical bounds. That's the reason behind the theoretical interpretation of this DeepONet or any scientific machine learning domain. But recently something came like pins are now used. People are using pin for that in silico trials. What does it do? Like already there are traditional methods where they simulate heart and find the solution. Now that take 3 days with some accuracy, but now they have developed one DeepONet method, surrogate modeling, through surrogate modeling, and that tells like it is solving in some minutes and with a very low margin of accuracy. Means what traditional solvers are giving and what that sorry, that scientific machine learning is giving is very nearly same. It's very low marginal error is there. So it's developing.
Um,
Yes.
but the training data that you have collected is through that equation only, right? Whatever. I mean, when
No,
you are
no.
training this kind of neural network,
It,
from where you're getting the training data?
okay, everywhere you can't assume like, okay, we have this underlying PD. So there are some solution already. Suppose you are one machine is okay, think like this. One machine is generating some output, and you are getting this output some time to time bound. Now you want to, okay, take for any weather prediction. Weather prediction is a very good application for this domain. So people have been shown like anima's group have been shown like they have used FNO for the weather prediction, and it is very accurate. It come on the natures also.
Okay.
So what they have, like, they have collected the weather predictions timely, that data they have
Okay.
collected, and you don't require to know the PD for that, right? And eventually you
Okay.
need to not know for any cyclone how the cyclone is coming. You don't know the PD. If you know, then
Right.
already you have been prevented. So there you have
Hmm.
already the training data. So just need
Hmm.
to use this kind of
Okay. Okay. Okay.
techniques, and then you are done.
Yeah, got it. Yeah. Okay. Yeah, understood.
And is it mainly used in physics? Means I was going through just physics field mainly. This all
Okay.
these things. Now I'm asking you. Mainly, I'm saying that they are that you said the term PIN and all.
Yeah,
They are
physics
saying that
informed.
with the
Yeah.
that
So
equations
so
and all put.
okay, for this
Yeah.
DeepONet, it is not using any physics property, you can see, but there are variations of DeepONet. So now it is coming like physics informed DeepONet, that is called PI DeepONet. So there, what we do, already you have been seen these laws, right? One second. Yeah, this loss, this LD ponent, this loss you are seeing. Now if you have the physics property, if you know the solution, then what you can do, you can append two more losses, loss term with it. One is your boundary value, and one is your initial value. So what you are already know the this is operator, you this deponent is a operator. So what will you do, you already know the solution at 0 comma 0, suppose like that. So you are you will measure the deponent 0 comma 0, and you have the solution for the initial, and you will measure the squared loss, that is one for the initial condition. And suppose you have the value for 0 comma t, when t is the initial condition, then you measure the value deponent 0 comma t, and you again measure the square loss. So three loss will be there. There you are using the physics property. If it is deponent, then you are not using any physics property here. But if you add your boundary value and initial value additionally, then there you are using the physics property. That is pins, actually, that comes from the pins exactly to that.
Okay. Anyone has any other question? Okay, then since no one has no question, so thanks Amartya again for your talk.
Yeah. Okay,
And
thank you.
okay, I think someone has a question. Yeah, you can ask them.
I just want to know like how old is the field and how frequent are this kind of researches being happening in this field?
Sorry, come again, your voice broke. I'm sorry again.
Hello,
Yeah, come
am
again.
I
Yeah,
audible?
yeah, now you're audible.
Yeah, I just want to know like how like popular is this field and how much frequent the research is happening in this field.
Okay, it's like okay, that chain and chain universal approximation theorem formula, this came in 1980s, I guess. But then nobody was like, was not into that. But suddenly some Brown University group, and if I remember correctly, Pedriakis, who reinvented this loss, who reinvented this kind of loss, and who refigured this. And from then it's 2017 onwards, pins, deponents, wavelet neural operators, all the kind of sort of Fourier neural operators, all sort of neural operators, and the scientific machine learning are buzzing. And this is more into industrialization. Like you can think like in any industry, they will need some PDE solution. Like in any industry, that may be wind, that may be a like atomic kind of scale of thing. Anyways, you need PDE. to get the solution. And for that you need this kind of methods. And for weather prediction it's a huge, and also now people are using in silico trials and also. Yeah, it's very buzzing and it's a very open area, and there are many things to prove. Now it's a very baby now. We need a lot more grooming for this.
Yes, and one thing that branch and trunk network you explained, uh, are they means in deep learning we use lots of layers in between.
Yeah.
It's dependent on that model thing. Here also there are lots of layer, or it's specific. Means, am I
No,
getting?
yeah, you are correct. In think like this, branch is your one neural net and trunk is
Yeah.
your another neural net. Now, whatever design you want, you can design your neural net. That doesn't depend anything, and that doesn't matter also for us. We want for this theorem, we want just that your output layer will be bounded by sigmoid. That's it. In between, any kind
Yeah.
of layers, any kind of activation you can use, and that will for that also for that architecture also this theorem will hold.
So, so
Yeah, you can ask the question. Yeah.
yes. So I mean, on your design. So, do we have any mathematical software or something to map these kind of things,
Yeah,
or
we
it
have.
just they are in?
NVIDIA already has released DeepONet libraries and all. Already there are many implementation in JAX. JAX is kind of a Google-based library for this automatic differentiation and all. So JAX is a very prominent library for DeepONet, and also NVIDIA has a page for the scientific machine learning thing. There you can just plug and play with this.
Okay, so so I understand that, but but what's the physical implementation of this? Because we know that how we can design that and how these networks are formed. So those, as you have already mentioned, that there's theories also, so theorems and algorithms also in this. So how you see the use of it? Because they all are in theoretical perspective only.
Uh, no, actually not in theoretical perspective. These in industry, not in many industries, they are using this kind of scientific machine learning for faster productions. Say for now, what as far as I know, in silico trials, people are using this. In weather prediction, people are using this, and these are more accurate. There is one lab, PNAS lab probably, and they are uh, very much deep into this research, this scientific machine learning research. So what the thing is, we need to know more the theory about this. Unless we don't know the background and we don't know the main theoretical concept of these, we can't improve the structure. And also there are many things. Suppose there is a lacuna of DeepONet, also there is a lacuna of pins also. Like those need to be covered to theory only. So think like that. You for a LLM, any kind of LLM, if you do, then you don't know like how to tune your LLM so that it will finally converge. You don't know the training data, how much training data you need. You just arbitrarily feeding the training and all. So the same occurs here also. There are many areas in DeepONet and in scientific machine learnings where we exactly not know how we can set the branch and trunk layer so that the accuracy will drop and so that we can get a good accuracy and all. So there comes the theoretical perspective.
Thanks.
Okay. Any other question? Okay. Okay. Thanks again, Amartya, for this
Yeah,
nice
thank
talk.
you.
And thanks everyone for joining. So we'll again meet next week, Friday this time, for another exciting talk. Okay. Bye.
Thank you
Goodbye.
all. Bye.
Bye.
Thank you.
Thanks. Thank you.